Hi, I'm Janice.
I'm Joanna, and today we're going to talk about slender columns and principles of reinforced or press-stressed concrete. What is a slender column? A slender column is defined as a column that has a significant reduction in its axial load capacity due to moments resulting from lateral deflections of the column. These columns have a great tendency to buckle, especially if there is eccentric loading that causes bending moment. Its greater tendency to buckle increases the effect of bending moment in the column. Thus, moment is larger. Because of the increase in maximum moment due to deflections, the axial load capacity is reduced. This reduction in axial load capacity results from what are known as slenderness effects. Slenderness effects can also be defined as the effect of buckling. Let us consider this column in a state of neutral equilibrium. Because our column is prone to buckling, we need to consider the effects of buckling. Thus, the equation for deflection is EI times d squared y over dx squared equals to negative py, where negative py is the bending moment due to deflection. In the year 1744, Leonhard Euler derived a solution known as the critical buckling load. P sub c equals to n squared times pi squared times EI, all over L squared. Where EI is the flexural rigidity of column cross-section, L stands for the length of the column, and n is the number of half-sine waves in the deformed column shape. Column effective length is also defined as the length of a pin-ended column having the same buckling load. Variable n, or the number of half-sine waves, is simply the curvature of the column. This bend shape usually happens in the parts of the column without support. The effective length is expressed as KL is equal to L over N. The effective length factor is given by K is equal to 1 over N. Using the concept of effective length, the critical buckling load becomes P sub c is equal to pi squared times EI all over KL squared. Look at the figure on the screen. The effective length of the column in figure B is the same as that of the column in figure C. There are two kinds of frames. First is the braced or non-sway frames, which is defined as frames prevented against deflecting laterally. These frames are stiff enough not to move laterally. This means that when axial load is applied to the column, it will not have lateral movement as column bends due to axial loading. Second is the unbraced or sway frames, which is defined as frames that sway laterally when columns buckle. These frames are not stiff enough, which means that when axial load is applied to the column, it will move laterally. There will be deflection, which is caused by the movement of the floors. Here are some important points to consider in practical application of these principles. In actual structures, fully fixed ends rarely, if ever, occur. Pin-ended columns are rare in cast-in-place concrete construction, but do occur in precast construction. Most concrete building structures are braced, non-sway frames, with the bracing provided by shear walls, stairwells, or elevator shafts that are considerably stiffer than the columns themselves. Most building columns fall in the short column category. Exceptions occur in industrial buildings and in buildings that have a high first-floor story for architectural or functional reasons. Let's proceed to the behavior and analysis of pin-ended columns. Usually, the behavior analysis of columns is based on a simple hinged column. Lateral deflections of a slender column cause an increase in the column moments. Increased moments increase deflections that further increase the moments. There are two kinds of analysis. The first-order analysis, which is used in the analysis of short columns, is when equilibrium equations are derived by assuming that deflections are considered to have a negligible effect on the internal forces in the members. The second-order analysis is when equilibrium equations consider the deformed shape of the structure. Deformed shape has something to do with the deflection, so the structure can be statically indeterminate. Due to geometrical incompatibility, we need to take into account the deflection. This is used in the analysis of slender columns because deflections add to the effects of bending moment to the column. Instability of the structure due to buckling can only be analyzed by second-order analysis. Because the excessive buckling in columns causes instability in the structure, we need to take into account the effects of buckling. Additionally, first-order moments are bending moments that causes stress to the columns, while second-order moments are moments that are based on deflection. There are two different types of second-order moments act on the columns in a frame. First is the P small delta moments. These result from deflections of the axis of the bent column away from the chord joining the ends of the column. The slenderness effects in pin-ended columns and in non-sway frames result from P small delta effects. Second is the P capital delta moments. These result from lateral deflections of the beam column joints from their original undeflected locations. The slenderness effects in sway frames result from P capital delta effects. Take a look at the figure on the screen. The P small delta moments are moments caused by buckling, while the P capital delta moments are caused by sidesway, or the movement of the floor relative to each other. Load moment curves for columns with three different lengths. Columns are loaded with increasing axial load, P, at constant eccentricity, E, until failure. That is, curve intersects the interaction diagram. Take a look at the figure. Curve 0 to A represents a short column. Curve 0 to B represents a moderate length column. Curve 0 to C represents a very slender column. For the column of moderate length, curve 0 to B, as the axial load P increases, the deflections become significant, reducing the failure load. This column fails when the load moment curve intersects the interaction diagram at point B. This is called a material failure, and is the type of failure expected in most practical columns in braced frames. For the very slender column, curve 0 to C, with increasing axial load P, a deflection small delta may be reached at which the value of the small delta m over small delta P approaches infinity, or becomes negative. When this occurs, the column becomes unstable, because with further deflections, the axial load capacity will drop. This type of failure is known as a stability failure and occurs only with very slender braced columns or with slender columns in sway frames. This type of column means very thin column, which also means greater tendency of buckling because the center of gravity will shift, and it will fail not due to material failure, but due to instability. For a symmetrically loaded pin-ended column, the first order deflection, small delta sub O, is due to the end moment m sub O8. The application of axial load P increases the deflection by small delta sub A, thus, the total deflection or second order deflection is expressed as small delta equals small delta sub O plus small delta sub A. The final deflected shape of the column is due to the second order moment m sub C, or maximum bending moment, and is expressed as m sub C equals m sub O plus P small delta S. Because slender columns can either fail due to material failure or instability, we need to consider the derivation that will be incorporated in our design. When designing slender columns, we need to increase the moment. Thus, the original moment plus the bending moment due to deflection. Thus, the formula m sub C equals m sub O plus P small delta S, where P small delta S is the deflection due to buckling, and m sub C is the total moment used in design. But instead of finding the deflection, there is a method for this analysis and computation. According to AC Code Section 6.6, 4.5, the formula of the second order moment is given by m sub C equals to small delta ns times m sub O, where small delta ns is the non-sway moment magnifier, m sub O is the first order moment, taken as the larger moment m2, and m sub C is the total moment that includes the effective deflection. So instead of finding the deflection, we just find the magnification factor. Also note that ACI Code Section 6.6.4.5.4 requires that the minimum value to be taken for the larger end moment, my, should be m2 minimum equals to P sub U times 15 plus 0.003 times h, where h is in millimeters. There is usually two end moments, the top and the bottom moments, where the moment at the top is usually less than the moment at the bottom. In design, we check if the m2 minimum is larger or lesser than the actual moment, because it is the minimum moment that should be used in design. The non-sway moment magnifier, according to ACI Code Section 6.6.4.5.2, small delta ns is equals to C sub m over 1 minus P sub U over 0.75 P sub C, which should be greater than or equal to 1.0. Where C sub m is the equivalent moment factor, P sub U is the total factored load in the column, and P sub C is Euler's critical buckling load based on ACI Code Section 6.4.4.2. Also note that small delta ns should not exceed 1.4 to maintain stability. The equivalent moment factor, C sub m, accounts for the effects of unequal end moments on slender columns in braced frames. Thus, C sub m is equals to 0.6 minus 0.4 times m1 over m2, where m1 is the smaller end moment and m2 is the larger end moment. The equivalent moment factor, C sub m, is incorporated because columns have unequal end moments. The equivalent moment factor will convert these moments into uniform bending. As you can see in the figure in A is the actual moments at failure, and the figure in B is the equivalent moments at failure where C sub m is incorporated. Also note that m1 over m2 is negative when the column is bent in single curvature, and it is positive when the column is bent in double curvature. Applications for the equivalent moment factor equation. First is hinged columns or columns with pinned ends. Second is columns in braced frames. There are also cases where C sub m equals to 1. First is for columns subjected to transverse loads between their ends. Second is for concentrically loaded columns, columns with no moments. For the next part of our lesson, allow me to give the floor to Janice to further discuss the latter part of this topic.
Thank you, Joanna. In the succeeding slides, we will talk about the different aspects of a column. So what exactly happens to a column? A column is exposed to a compressive load at which it may suddenly bend or buckle. This compressive force is called Euler's critical load, denoted as P sub C. In calculation of the Euler critical load, P sub C involves the use of the flexural rigidity, EI, of the column section. The value of EI is taken as an approximate value at the time of failure, which takes into account the 1 is the type of failure. It may be material failure or stability failure. 2 is the effects of cracking, creep and nonlinearity of stress-strain curves at failure. Formulas of EI to the computation of critical loads for individual columns are as follows. EI is equal to 0.2 E sub C times IG plus E sub S times ISE all over 1 plus beta DNS. The other one is EI is equal to 0.4 E sub C times IG all over 1 plus beta DNS. You can pause the video to see in the screen what is the meaning of the symbols in the formulas. In some other cases, most columns and structures are sufficiently short and stocky to be unaffected by slenderness effects. According to ACI Code Section 6.2.5 and SCP Section 6.2.5, slenderness effects can be ignored if the following equations are satisfied. For braced or non-sway frames, KLU over R is less than or equal to 34 plus 12 M1 over M2. For unbraced or sway frames, KLU over R is less than or equal to 22. where LU is the unsupported height of the column, and R is the radius of the gyration. And 34 plus 12 m1 over m2 should not exceed 40. And now, it is shown in the figure are the values for the effective lengths for columns in sway and non-sway frames. Let's talk about column unsupported length, the LU. It is considered to be equal to the clear distance between slabs, beams, or other members that provide lateral support to the column. If haunches or capitals are present, the clear distance is measured from the bottoms of the capitals or haunches. In braced frames, column deformation is restrained in two ways. The first way is the horizontal deflection of one end of a column relative to the other end is prevented by walls or other bracing elements. The second one is beams attached to the columns restrain the rotations of the ends of the column. The actual value for K in an elastic column is a function of the relative stiffnesses, psi, of the beams and columns meeting at a joint, ACI Code Section 6.2.5 and NSCP Section 406.6.2.5. Psi joint is equal to the summation of EI over L of the columns over the summation of EI over L of the beams, where LB and LC is equal to the length of the beams and columns measure from the center to center of the joints. The IC is equal to 0.7 Ig and IB is equal to 0.35 Ig. And the theoretical values for psi is 0 when it is fully fixed and infinite if the end is pinned or perfectly hinged. And in practical structures, there is no such thing as a truly fixed end or a truly hinged end. Reasonable upper and lower limits on psi are 20 and 0.2. K values for columns in non-sway frames are never taken less than 0.6. Calculation of K can be taken from nomographs or alignment charts like shown in the screen. And now let's proceed to moment magnifier method, sway frames. A sway, unbraced, frame is one that depends on moments in the columns to resist lateral bonds and lateral deflections. The total moments at the top and bottom of all the columns must equilibrate the applied lateral load moment VL, and moment due to vertical loads, summation of P delta. And in a sway frame, columns in a story deflect laterally by the same amount, therefore, it is not possible to consider columns independently. Stability of the frame requires that full magnified end moment from the columns be resisted by beams. There are two types of moments occur in frames. One is the moments due to loads not causing appreciable sway, MNS. 2 is the moments due to loads causing appreciable sway, M2. The slenderness effects of the two types of moments are considered separately in the design process because each is magnified differently as the individual columns deflect and as the entire frame deflects. Unmagnified non-sway moments, MNS, are added to the magnified sway moments, delta SMS, at each end of each column to get the total design moments. For the sway frame moment magnifier, delta S is equal to 1 over 1 minus summation of PU over 0.75 summation of PC, and it should be greater than or equal to 1.0, where the summation of PU is the sum of all axial loads of all columns in a story and summation of PC is the sum of all critical buckling loads for all columns in a story. And for the critical buckling loads, it is calculated by using effective lengths, evaluated for columns in a sway frame. Formulas of EI for the computation of critical loads for the individual columns in sway frames. EI is equal to 0.2 E sub C, Ig plus E sub S, ISE all over 1 plus beta ds. EI is equal to 0.4 E sub C, Ig all over 1 plus beta ds, where beta ds is equal to maximum factored sustained shear in the story over the total factored shear in the story. In order to guard against instability, the code limits the ratio of the second-order moment and the first-order moment to 1.4, ACI Code Section 6.2.6. For non-sway frames, MC over M2 is less than or equal to 1.4. And for sway frames, M2 over M2NS plus M2S is less than or equal to 1.4. In practice, a structure is seldom either completely braced or completely unbraced. Therefore, it is necessary to determine in advance if bracing are adequate to restrain the structure against significant sway effects. The code provides criteria for determining if columns and stories are treated as non-sway or sway. First is a column is considered non-sway if the increase in column end moments due to second-order effects not exceed 5% of the first-order end moments. The designer is free to select the method for determination. Second is a story is considered non-sway if the stability index Q is for a story is not greater than 0.05. Stability index Q is equal to summation of PU times delta O all over VUS times LC, where summation of PU is the total factored vertical load for the story, VUS is the total horizontal shear of the story, delta O is the first-order deflection between the top and the bottom of the story due to VUS, and the LC is the length of the compressive member measured from C to C of the joints in the frame.